So yesterday we abruptly stopped while we were doing this example, trying to interpret permanent as a graph, right? So permanent is defined via sum of monomials, and each monomial we want to see as a cycle cover. Now the monomial corresponds to a permutation of 1 to n, which are the vertices. So permutation, you can see it as decomposing into cycles, and that is what you can visualize as a cycle cover in your graph, in the graph which is defined by E as an adjacency matrix. So the example is that we were doing vertices 1, 2, 3, and there are these 8 weighted edges. There are no self loops. So it actually gives you 3 cycles, and hence 3 cycle covers. Sorry, not 3, 2. So there is this clockwise 1, 3, 2, 1, and the anti-clockwise 1, 2, 3, 1. First has weight 1, second has weight -1. So which means that the permanent of this matrix comes out to be 1 minus 1, which is 0. Okay, and this you can check that by definition also it's 0. And the same thing you can see in terms of cycle covers and sum of weights of cycle covers. So once you have seen this, now comes the use of this interpretation. The use will be quite stunning. So we'll actually use this graph to show that permanent is the hardest problem in counting class, sharp P. So our theorem is that permanent for 0, 1 matrices is sharp P hard. So essentially we have to show that sharp 3 sat reduces to permanent. Sharp 3 sat can be reformulated as a permanent question. We relate sharp 3 sat to permanent. So let phi be a 3CNF formula with m clauses n variables. And we can assume that without that each clause has exactly 3 literals. Right, a clause may have 2 literals or 1 literal, but then we can repeat it. So without loss of generality, each clause has 3 literals. So there are these m clauses, each has 3 literals, so it's 3m occurrences of literals. Variables are n, x1 to xn. So the idea is construct a graph A construct a graph via an adjacency matrix A such that the sum of its weighted cycle covers equals permanent. I mean, which is also permanent by the previous interpretation, is the number of satisfying assignments of phi. Okay, so we want to relate sharp 3 sets. So basically, we want to count the number of satisfying assignments that will make equal to permanent. We'll construct such a matrix. Constructing this matrix with 0, 1 is pretty difficult, if not impossible, to imagine. So we'll actually get this done by drawing graphs, and those graphs will look complicated. Okay, we'll introduce gadgets, graph gadgets, to express literals, to express variables, literals, and clauses. So let's see the implementation of this idea. So each variable xi is converted to a graph gadget vi So the graph gadget will this we are doing it for variables, right? So this variable gadget will have to be connected to the gadget for the clauses, and there are m clauses. So we'll actually have m parts in this vertex gadget. So let me draw that. So these self loops and connected via m edges. These are m plus 1 vertices. Here, and so there are m plus 1 self loops here, and 2 more vertices to capture truth and falsehood of the variable, truth or falsehood, right? So that's the full gadget. What are the weights? So weights of all these edges is 1. Every weight is 1. This is the true, and this is the false. Okay, so the edge below one is the truth. If it is used in a cyclic cover, then it means that the variable is set to true. If the top edge is used, then the variable is set to false. That's the meaning. That's the interpretation of this. And these ones, these are the m external edges, we call them. So what is happening is, if you use the external edges, then you will have to use the true edge. If you do not use them, then you are using the self loops, and you will be forced to use the false edge. Okay, so in this way you can set the variable true or false. That's the interpretation. How it fits in the big picture, that we will see later. So let me write what I just said. The interpretation is the cycle cover using external edges of Vi signifies excite set to true. Okay, while the other while others signify that xi is set to false. Okay, so if the external edges are used, then true edge will be used. So we interpret it as setting xi to true or 1. Otherwise, we are using the self loops and the false edge interpreted as xi equal to false or 0. Now, each clause let us say fj, the jth clause, is converted to a graph gadget ci cj, which is yeah, this will actually look simpler than the vertex gadget. So here what we will do is, remember the clause, each clause has 3 literals. So we will kind of add here 3 cycles depending on which literal has become true. So it will be like this. And then the internal connections. So these are the external edges. These are 3 external edges instead of m plus 1, because now we are focusing on the clause, and the clause gadget has interpretation, it is related to 3 literals. So there are 3 external edges, and the internal connection is as follows. Okay, so as always, unmarked weights are 1. Just assume that. Unmarked edges have weight equal to 1. So what is the interpretation of this? So here there are 3 cycle covers. So could you see these 3? Basically, you can use one external edge, then 2 internal edges, and another external edge. That will give you a particular cycle, and you can do this in 3 ways. So there are 3 cycle covers, each of weight 1. Each corresponding to a dropped external edge. And the latter, the one which is dropped, that means interpretation is that that variable is, or literal is, set to true. So the latter signifies that the corresponding literal in Fj is true. Okay, the one which is dropped. So here, so for example, one example cycle cover is you can pick this, and then you can pick this, then you can pick this, and you can pick this. Okay, so in this case, the dropped one becomes this. Right, so here is a cycle cover. These yellow edges which I have marked, this gives you a cycle because it is cycle cover because it is covering all the 4 vertices here, and it leaves one external edge which we are thinking of as literal set to true. Okay, so always a cycle cover here in the clause gadget means that signifies that the clause is true because some literal is true. But these two things currently are independent, right? We drew a variable gadget and we drew a clause gadget, but this information has to be connected. So we also need a connecting gadget. So if xi in Fj then the jth external edge of Vi, the vertex gadget Vi, is connected to the xi external edge Vv prime of the clause of clause gadget Cj. By a new gadget which we are calling XOR. Connecting I to J. So vertex ith vertex gadget to jth clause gadget, you have to make a connection. The 2 external edges have to be matched. So that is done by XOR. So this is the most complicated gadget because it will connect these 2 much simpler gadgets. Connection means what will connection force? The connection will force that this interpretation that if xi is set to true and xi appears in Fj, then Fj should be true. Okay, so any cycle cover should actually pass through the right external edge of xi of Vi, and the right external edge should be dropped in Cj. So that will be done as follows. So let me draw it first, then you try to understand what is happening. So there are these 4 vertices forming a cross. So U is connected to this and U prime is an out edge. The opposite here. Then I give self loops to these ends, and I give a loop here. I give a connection here, and I give a cycle. And I also give opposite edges only here. Now interestingly, here we will also need some negative weights other than, I mean, unmarked ones are 1, but we'll also need -1 and 2 and 3, because we'll want the cycle cover contribution of this connecting gadget to be 0. That's why. I need one more edge, give it 3. So again, the interpretation is let me first also make this definition complete. So if xi is literal in fj, then we'll connect the jth external edge of vi, which I think we are calling it uu prime. So the jth external edge in the vertex gadget, okay, if that is uu prime, then this is how the connections are done. So uu prime is shown in your XOR gadget, and then vv prime, which is the one of the 3 external edges of the clause gadget, that's also shown in this XOR gadget. Okay, so this will allow you to basically pass from vi through the XOR gadget to Cj. That's the idea. And maybe xi bar is a literal, so then we'll do something else. So if xi bar is a literal, then the false edge, because xi you are forcing it to be, you want to force it to be false, right? So you have to now work with the, not the external edge, but the false edge. Then the false edge uu prime of vi is connected to xi external edge like before. We are calling it vv prime of Cj. This is done by XOR ij. Okay, so this completes the definition. You use this XOR gadget to connect the correct edge of vi to the correct edge in Cj. And let me give the interpretation. So here the interpretation is the appropriate truth or false value of xi forces the correct cycle cover to be picked in Cj, right, which corresponds to Fj, and xi corresponds to Vi. So path that you are taking inside Vi, that actually forces, that corresponds to truth or falsehood of Xi, and then it gets transferred via the XOR gadget to the clause gadget Cj. Okay, that's the idea. This UU prime gets transferred to VV prime in the language of cycle cover. So the final graph looks like the big picture after all these small gadgets are connected. The big picture is so the graph A prime in the big picture is you have the vertex gadgets, you have the clause gadgets, and Vi and Cj connected via XOR gadgets. But remember that Cj has 3 literals, right? So Xi is just one of them, Xi or Xi bar. So other 2 are also present like this. Okay, and so on. So that's the interpretation. So these are the vertices. These are the clause gadgets, and in this layer you have the XOR gadgets. Okay, so these are the gadgets. So as you can imagine, n vertex gadgets, m clause gadgets, and 3m XOR gadgets. So let's fix our understanding in this claim. Till now what we have done is there are n vertex gadgets, m clause gadgets, and 3m XORs. That's obvious from this picture, from the big picture. Second claim is that the cycle covers of XOR sum to weight 0. Okay, so remember that if you want to compute the permanent of this graph, that's a complicated formula. So we will break down the calculation into smaller parts. So first we'll analyze it gadget by gadget. So we will look at the contribution coming from XOR, and that we have made sure is 0. That is what I will prove. And the other contributions from the vertex clause gadgets you can see is 1. So it will help us in doing the counting in this graph. So and remember that these edges which are unmarked, they all have weight 1, right? The other than 1, we have -1, 2, and 3. So there are only 4 possible values. And obviously 0, if there is no edge, then it's 0. So it's either 0, 1, 2, 3, or -1. Those are the values of edge weights. And let's now see what is the contribution of XOR gadget minus UU prime VV prime. So cycle covers in XOR gadget minus UU prime and VV prime because UU prime, VV prime are actually in other gadgets, right? These are vertices in other gadgets. The vertices of XOR, how much are they contributing? Let's do that. So you can either use the self loops of XOR or not. And then there are these forward edge, backward edge. You can use that or not. So accordingly, you will actually get 4 cycle covers. Let me write that down. You can verify later. So the first cycle cover is, it looks like this. So I am drawing it so that it's easy for you to verify. This is the top left forward backward and the bottom right forward backward with weights 2, 3. There are only 4 vertices, right? So this covers all 4 of XOR. Next is so next is now the full cycle, which goes like this. So the exceptional weights are -1, 2, and the rest is 1. And 2 more, so we'll do this soon.